folks, today we're going to continue our discussion on different things we can do with complex numbers. We'll start with talking about powers of complex numbers. I'm going to jump right in here. So this, remember from yesterday, is the general form of a complex number, general polar form of a complex number. So if I take z and multiply it by itself, that would be r cosine theta plus I sine theta times r cosine theta plus I sine theta. So on the left here we have z squared, and on the right we're just multiplying two complex numbers together. We talked about that yesterday, and we said when you have the product of two complex numbers, you multiply the r's together and you add the thetas together. So we have cosine 2 theta plus I sine 2 theta, and that is equal to z squared. If I then take z squared and multiply that by z, I now have r squared cosine 2 theta plus I sine 2 theta times r cosine theta plus I sine theta. And again, if I follow the rules of multiplying complex numbers together, right, on the left I have z cubed, and then on the right r squared times r gives me r cubed, and I add my thetas together. So 2 theta plus theta gives me 3 theta. And so I can keep doing this over and over and over again, and what it eventually brings me to is de Moivre's theorem. And hopefully you guys can see this. It's a little bit small on the screen, but it is on your paper. So I'll just write it over again. We've got z to the n. So whatever power n is, r is raised to that same power, and then your theta is multiplied by that n value. Sine of n theta. Okay, so it's really pretty easy to use. Let's go through, we'll do a couple of examples. In this first example, it says to find this complex number raised to the 6th power. Okay, and I'm going to actually, we'll write it in polar form first, and then I'll go all the way through to rectangular form. Okay, so if I follow de Moivre's theorem, that means I'm doing 2 to the 6th because it's the 6th power, and then I have cosine of 6 times pi over 18 plus I sine of 6 times pi over 18. Okay, and 2 to the 6th would be 64. Now I end up with cosine, right, of pi over 3 when you reduce that, plus I sine of pi over 3. And that would be your answer in polar form, but if I want to take it all the way through to rectangular form, I have to actually evaluate cosine of pi over 3 and sine of pi over 3. So I end up with 64. Cosine of pi over 3 is 1/2 plus I times root 3 over 2. And so if I distribute that 64, I end up with 32 plus 32I root 3. And that would be your final answer. We always write the I before a radical, but after a number. Okay? Okay, let's look at the second one. If I go ahead and go through that same process, I end up with 3 to the 4th times the cosine of 4 times pi over 6 plus I sine of 4 times pi over 6. Squeeze that in there. So 3 to the 4th is 81. Cosine, I end up with cosine, when I reduce that 2 pi over 3 plus I sine of 2 pi over 3. And so if I evaluate that and distribute, cosine of 2 pi over 3, that's in the second quadrant. Cosine is negative in the second quadrant. That would be the cosine of, same as cosine of 60, so that's going to be negative 1/2. Sine is positive in the second quadrant, so this is going to be positive I root 3 over 2. And so my final answer then when I distribute that 81 is negative 81/2 plus 81 root 3 over 2 times I. And you could have written I in the numerator, but I just pulled it all the way out because I had a fraction there. But that is your final answer. Okay, so that's how you would use de Moivre's theorem and raising complex numbers to different powers. Let's talk about finding the power of a complex number when you've got something in rectangular form to start, right? These were in polar form to start, but now we're in rectangular form. Okay, so the first thing we need to do, because we can only use de Moivre's theorem, but we can only use de Moivre's theorem when we're in polar form, so we have to actually convert this first into polar form. Okay, so remember to do that, I need r and theta. And from what we did yesterday, we know that r squared is equal to a squared plus b squared. So r is going to be the square root of a squared plus b squared. So then r is going to be the square root of 1 plus 1. So that's going to be the square root of 2. Okay. Then we also need theta. Remember, tan of theta is b over a. That would be 1 over 1. So that would tell us that theta is pi over 4. And the reason I know it's pi over 4 and it's in the first quadrant is because if you graphed 1 plus I, you'd end up over here in the first quadrant. Okay, so I have r and I have theta. So I know then that 1 plus I to the 8th is going to equal root 2 times the cosine of pi over 4 plus I sine pi over 4. That should be a square bracket there, to the 8th power. Okay, so I got my r value and my theta so that I could write it in polar form. And now I'm going to raise that to the 8th power. So now I can use de Moivre's theorem. So de Moivre's theorem says I'm going to take my r value and raise it to that power. And then I have the cosine of 8 times pi over 4 plus I sine of 8 times pi over 4. Root 2 to the 8th. Remember root 2, I'll write it over here. Root 2 is 2 to the 1/2 power. If I raise that to the 8th power, remember when you raise an exponent to a power, you multiply those together, so that gives you 2 to the 4th. 2 to the 4th is 16. So here I will have 16. And then I have the cosine of 2 pi plus I sine of 2 pi. And the cosine of 2 pi is 1. The sine of 2 pi is 0. So that would be 0i. So you end up with just 16 as your final answer for that one. Okay, so when you're in rectangular form, you got to convert it into polar form before you can apply de Moivre's theorem. Okay, so we're going to talk about roots of complex numbers. And we're actually going to work a little bit in reverse at this point, because now we're going to be finding the roots instead of finding the power. Okay, but let's talk in general terms first. We say that when if we have z to the n is equal to w, which is just some complex number, that means that z is an nth root of w, right? If you've got z to the n is equal to w, if you take the nth root of both sides, right, you end up with z is equal to the nth root of w. That's what this is saying. Okay, so if we then apply de Moivre's theorem, and I say let w equal r cosine theta plus I sine of theta, then I can go through setting up this idea of de Moivre's theorem in the reverse. So let me write that out for you, and then we'll talk about it a little bit. So I've got z to the k is going to be the nth root of r. So instead of raising everything to a power, we're now taking the root of it. And then we have the cosine. Now with raising to a power, remember we multiplied by n. But now we're going to, because we're taking the root, we're going to divide by n. But instead of just having theta over n, I end up talking about all different possibilities for theta. Now let me write this out and then I'll explain what it means. Because you know I'm not really good at talking and writing at the same time. And I'll write it in terms of degrees as well. So we've got the nth root of r times the cosine of theta plus 360 degrees times k over n plus I sine of theta plus 360 degrees k over n. So when we were raising to a power, we multiplied by n, but when we're taking the root, we're dividing by n, but we're taking all possibilities of that. And the reason that we have it, the reason that we have all these multiples of k is because we might only be taking one root. We might be taking cube roots, so there'd be 3 different answers. We might be taking 4th roots, so there'd be 4 different answers. So we have to account for that. That's why we have k in there. We did that way back when we were doing different things with trig, and we were finding all the possible solutions, and we would keep doing multiple revolutions. It's that same idea. In that depending on how many roots we have to be able to account for that. So I'm going to do a couple of examples in the next video, so hang tight and you can move on to the next video. Thanks guys.